scheduling algorithms, and say that for the scheduling there are some common goals. For the common goals we have famous policy enforcement and balance. We looked at the batch system schedulers. We said that they should optimize the throughput, turnaround time, and CPU utilization. For the interactive systems, response time is the important thing. Meeting user expectations, there is this definition of cheap and expensive. And for the real-time systems, the important thing is the meeting the deadlines about user data. With these in mind, we started looking at the schedule. We looked at the batch schedulers. First come, first served, shortest word and shortest remaining time first algorithm. We saw those. Then after those, we started looking at interactive systems. Konuşmayın ya. Uğultu olmasın. Uğultu olursa benim kulağım daha fazla. Bir otursana yerine. So interactive systems. Interactive systems. What was the purpose of the interactive systems? Is the stay responsive. Okay. If the user wants to interact with the system, the system should be interactive. Should be responsive. That was the main thing in mind. That's why we said that preemption is a crucial part of these interactive systems. So all of these scheduling algorithms, they are designed for interactive systems, and they all assume that the underlying system is preemptive. Preemption is available. The first scheduling algorithm was, if you remember, round-robin scheduling. In these type of scheduling algorithms, there is one key term quantum. What is quantum? Quantum is okay, a time interval. It is assigned for each process. Each process can take at most this much amount of time. Maybe let's say I don't know, maybe 10 milliseconds or sometimes 100 milliseconds. Okay, I don't know. It depends on the system, and we looked at the definition. We looked at how we calculate this value actually. It's a trade-off between quantum value is a quantum duration is a trade-off between what? Between responsiveness and between responsiveness and we don't call it throughput, responsiveness and CPU utilization, right? If you take your quantum time too small, then that means that you are spending most of your time with context switching, and your CPU utilization will not be that good in that case. We talked about this before the exam actually. So there must be a trade-off, reasonable compromise. We don't know what these values are, but I mean, if you are spending 20% of your time in context switching, ya konuşmayın ya. O ses kim o kalın sesli adam ya? Bayanlardan konuşuyor, tamam mı kendi aramda? Sesini dinleyerek konuşuyor. Kalın ses kulağımı tırmanıyor böyle. Fısıldayarak konuşun. Bilmiyorum, bir çaresini bulun, kulağıma gelmesin diye. So the 20% of time is context switching overhead. It might be too much. Sometimes it is not. Sometimes, for some systems, even 50% context switching time, it may not be too much. What kind of systems are these? These kind of systems might be very, very interactive systems. It is okay if I don't use most of my CPU time for the useful work, as long as the user is happy. Okay. So, but this is not a good overhead for the batch systems. Because for the batch systems, the idea is use that expensive computer system to do something very, very lengthy, very, very expensive. Okay. So you want to use that CPU very, very efficiently. But for this kind of computer, I mean, CPU utilization is not my first priority, because if I use my CPU 100% of the time, all the time, then the battery in the system will not last for more than 20 minutes. So for some cases it might be okay with this kind of overhead. So it is always a trade-off between responsiveness, CPU utilization, and other system resource utilizations. Quantum length. So you do say that the quantum length should be this much. So this is round robin. In round robin case, you start with a process, and if the quantum is up, then you switch to another process, then this process, then this process, and it goes that way. Once you are done with this process goes at the end of the queue, and you do this in a round robin fashion. Our second scheduling algorithm is the priority scheduling. We say that not all processes are equally important. Okay, some of them might wait for a while to be executed. Let's say if you are taking a backup of your system, or let's say if you are sending a mail, okay, email. Let's say you have 100 emails, and you need to send them one by one. So sending email is important, but it doesn't have to be done in real time. It doesn't have to be done in a responsive way. So if you send your email if you delay sending your email for 30 seconds, it doesn't matter much, because this is not online chatting or online talking. So for the email sending application or backup taking application, you might keep your processes with a low priority, but those interactive processes, they have to have the higher priority. So you assign your processes priorities. You would say that these processes are important. They need to stay interactive, so they need to be executed first, okay? And the others, they can wait until the higher priority jobs are done, okay? So the simplest version of this priority scheduling is this: always run the highest priority process first, okay? So this is the simplest version. In this case, the simplest version of round robin scheduling is like this, and it works. It is not bad. But the simplest version of priority scheduling has problems. What is the problem? Problem is this: if the highest priority process is CPU bound, okay, if it is using CPU all the time, that means that it will keep running all the time, and you will never run your low priority processes. Okay, you will never run your low priority processes. In that case, those processes will start to that. You will never run them. That's not a good thing. So simplest version, priority scheduling, does not work very well. So we need to modify this a little bit. And we talked about this last time. Actually, priority version is important to. Let's say we have three processes: H, M, and L. The priority of H is highest. Priority of M is in the middle between L and H, and priority of L is the lowest. H needs a lock, okay, but the lock is held by L, so H blocks. So since H blocks, there is no high priority job to be run, so the scheduler selects this M. M starts running, and if M is a CPU bound process, it will keep running, and it will never let this process to run because L has a lower priority. Okay. In this case, since L holds the lock, and it will not get any chance to use the CPU, it will never release the lock. If this one never releases the lock, this one will never run. But it has a higher priority than M. In this case, what is happening? H indirectly waits for M. Even though it has a higher priority, okay, H has to wait for M, which is called priority inversion. Okay, priority inversion. You have to complete M, which is a CPU bound process, to be able to go to H. If H is an interactive process and M is not an interactive process, okay, so let's say with an M you are calculating the all the digits of the number pi, 10 billionth digit of the number pi. So this is a CPU bound process. H is a word processor. It has to be interactive. So the word processor has to wait for the M to complete this job, which will take years to complete. This is a typical case of priority inversion. And this is not a made-up case. People have seen the examples of this problem on very, very rare cases. On some space vehicles, we had seen these problems happening. Okay? So a priority inversion problem is a problem with the priority scheduling algorithms. Okay, there is one solution to this problem. The operating system Pintos, it solves this problem by using this priority donation technique. Okay, what it does is when H waits for a lock, okay, held by a lower priority thread L, H donates its priority to L. So when H says that I need this lock, but this lock is held by some other process, so H donates its priority to the lower priority process, and since lower priority process has a higher priority now, it will start running. When L releases the lock, H takes back the donation, priority donation back, and it can continue. So this is called priority donation. Okay, Pintos implements this priority donation for locks. Okay, so that's one solution. There are other solutions. Priority. So there is, when you implement priority scheduling, okay, you don't keep your priorities fixed for all the processes all the time. You should change them. You should change them as the process is executed. Because if you keep the priorities same all the time, you will run into those kind of problems, like the priority inversion, or the highest priority job gets the CPU, the others doesn't get it. So periodically, we reduce the priorities of the running processes, so that the lower priority jobs get some CPU time. So you reduce the priority of the running processes. If they run too much, that means that their priorities will get lower and lower. At the end, eventually, it falls below the priority of the next process. Next process in priority. Okay. Or the alternative is increase the priority of non-running processes. So so this is called process aging. If your high priority is aging, it loses its priority, okay? If your low priority process is aging, it will gain some priority. Or you can do both. You can reduce the running process priority, or increase the priority of the lower level priority processes. So this is called priority adjustment, and it addresses this problem. Okay, the simplest version has this problem of always running the same process. So this solves this problem, priority adjustment. Okay, any questions? Okay, if there are no questions, maybe we can continue. There is one technique that automatically adjusts the process priority according to its recent history. Okay, it says that increase the priority of non-running processes, decrease the priority of running processes. So it is doing both of them. Okay, it decreases the running processes and increasing the non-running processes. So how does it do this? It says that boost priority of I/O bound processes. Okay, boost priority of I/O bound process. When you have an I/O bound process, that process does not use CPU much, because it spends most of its time waiting for some I/O to complete. Right? So it says that I should increase the priority of the I/O bound processes and decrease the priorities of the CPU bound processes. Okay, so this is the main idea. Let's go back to the beginning of this scheduling. This maybe around here. Yes, maybe. So this is a I/O bound process, and this is a CPU bound process. So if you look at the CPU bound process, it is using CPU most of the time. But this one has very, very large gaps between the CPU usage. So this one is not using CPU much. This algorithm says that increase the priority of this type of I/O bound processes and decrease the priorities of these CPU bound processes. That's the idea. If I do that, I will let this process use CPU more, so it will get enough CPU time if I do that. Okay. So let's go back to slide again. That's the reason why we are boosting the priorities of the I/O bound processes. And this is the rule that they are using. If the process uses 1/f of its quantum, let's say if it is using 1/10 of its quantum or 1/25 of its quantum, boost its priority proportional to f. So if I am using 1/25 of my fraction of the last quantum, then my priority will be 25, very, very high. Why? Because I did not use much of my quantum time, so my priority is high. As soon as my data is available, I will start using the CPU. But if I use the whole quantum, then that means that if I use the whole quantum, that means that, so what would be the priority if I use the whole quantum? If I use the whole quantum, my priority will be, if I use 1/25 of my quantum, okay, my priority will be 25. If I use the whole quantum, what would be my priority? It should be 1, right? Because I am using 1/1, the whole quantum. I use too much CPU, so my priority will be 1, and that means that my priority is low compared to this one. So this technique is trying to let processes use equal amount of fair amount of CPU time. Because if I keep those priorities of those two processes, CPU bound process and the I/O bound process with the same priority, the CPU bound process will use the CPU most of the time, and the other one will have to wait for the I/O things to happen and also for the CPU bound process to finish its job. So this one is saying that if you cannot use the quantum, because you are blocked due to some input-output task, then you will get the more priority. So that's the idea. Okay, understand this one? So this is a dynamic priority adjustment technique. It will try to keep the balance between different types of processes.
Hocam son dediğinizi tam olarak anlayamadık. Türkçe ifade etme şansınız var mı? Biraz karmaşık geldi.
Nereden biliyorsun anlamadık var?
Ben anlamadım.
Ben anlamadım. Anlamış sorun.
Hocam şimdi yüksek öncelikli olanı az süre mi veriyor? Diğerlerine çok mu veriyor?
Neden sonra?
25'te 1'e bölüyor ya puanlama.
Bir tanesi 25'te 1'ini kullanmış. Evet.
Diğerleri de öyle mi kullanıyor yoksa?
Hayır, tabii ki 25'te 1'i kullananlar sadece 25 veriyor. Eğer 50'de 1'i kullandıysan o zaman 50 vereceksin. Şeyi ne kadarını kullandıysan, kuantumun ne kadar azını kullandıysan, tamam mı? Priority'ni o kadar arttırıyor. Eğer kuantumun hepsini kullandıysan, o zaman priority çok düşük oluyor. Sen diyor yeteri kadar zaten CPU'yu kullanmışsın diyor. Yani bir tanesi I/O bound oldu diye CPU'yu az kullanmasını izin vermek istemiyor. I/O bound çünkü CPU'yu az kullanıyor. Adamın işi disk beklemek, işte klavyeyi beklemek, mouse'u beklemek falan, tamam mı? Eğer adamın görevi bu diye buna CPU'yu az kullanma cezası veriyorsan adaleti kaybediyorsun bir proses arasında. Öbürü pi sayısını hesaplıyor adam, tamam mı? Ya da bir tane nümerik hesap yapıyor. Her şey elinde. I/O yapmasına gerek yok. CPU'yu aldığı zaman hepsi olduğu gibi kullanıyor. Bunların priority'leri aynı olmamalı diyor. Kuantum, adam eğer diyor şeyi kullanamadıysa CPU, bir sebebi vardır, ona daha fazla şey vereyim. Verimsizliğe yol açar mı peki bu? Çok fazla kompleks switch'e yol açar mı?
Ay öyle şey.
Bir de I/O bantlarda aralarda çok boşluklar vardı. O sırada
Tamam.
büyü boşa çıkmıyor mu hocam?
Evet, güzel. I/O band'da bir sürü boşluklar var. O boşluklar boşa gidecek diyor arkadaş. Ne diyorsunuz?
Diğerde de gidiyor sanki. Diğer türlü de gidiyor. Yani sıra geç gelince yine aynısı.
Hayır.
Yani
O boşluklar boşa gitmiyor.
O
Başka
boşluklarda
proses mi?
O boşluklar boşa gitmiyor. Niye? O boşluklarda CPU boş beklemiyor ki, switch ediyor. Başka bir yere bekliyor.
Aynen o yani ayağı gelmiş sonuç.
Boşa, daha zaten boşa gitmiyor yani onlar. O boşluklar boşa gitmiyor. Peki I/O bound bir şeyin prosesini arttırdığı, priority'ni arttırdığınız zaman CPU oralarda boşta beklemek zorunda kalmayacak mı?
Hocam zaten yapıyorsa tekrar söyleyecekler.
Tekrar switch etmeyecek, ona izin vermeyeceksin zaten. Scheduler'ını çalıştırmayacak ki zaten block bu. Yani I/O bound bir prosesin priority çok yüksek diye block bir prosesi başlatamazsın ki. Block bir proses zaten block'tır. Bekleyecek o.
Ama
Priority scheduling ne yapıyordu?
şeyi sağlam.
Priority scheduling'in temelinde ne var? Priority'leri yüksek olanları, öncelikleri yüksek olanları ilk önce çalıştırıyor değil mi? İlk önce onları çalıştırıyor. Eğer onların hepsi birden block olurlarsa işleri bitirirlerse öbürlerini çalıştırıyor. Yüksek priority'lerin hepsi birden blocksa eğer, düşük priority'leri çalıştırıyor. I/O bound bir proseste eğer blocksa ve priority yüksekse, blocksa o zaman daha düşük priority olanlar çalıştırılacak. Yani bir verimsizlik yok bunda.
Ama hocam bu interaktif, daha fazla interaktif olmasını sağlamayacak mı bence burada? Çünkü I/O bu sefer hazır olduğunda hemen almış olacak cevabı yani.
Evet, şey hazır olduğu zaman, datası hazır olduğu zaman, tamam mı? Diğerleri kadar datası hazır olduğu zaman bir interrupt geldi. Data hazır dediler. Scheduler orada datası hazır, bunun priority'si daha yüksek, öyleyse ben bunu çalışayım diyecek yani.
O yüzden interaktiflik daha fazla artmış olmuyor.
I/O bound olanlar için.
Evet.
Yani interaktifse tabii ki.
Evet.
İnteraktif bir proses değilse nasıl atacak ki?
Evet.
İnteraktif bir proses değilse atmayacak tabii.
Hocam kuantumu daha bitmemiş bir proses devam ediyor ama priority'si yüksek bir şeyin interrupt'ı geldi. Kesiyor mu kuantumu orada?
Priority yüksek bir şeyin interrupt'ı geldiği bir şey yok.
Yani IOS'unun interrupt'ı geldi.
Şimdi I/O hazır diye bir interrupt geldi sana.
Evet.
Değil mi? Ne oldu? Çalışan proses interrupt tarafından durduruluyor. İşletim sistemi de tekrar kontrol. İşletim sistemi datayla ilgili ne yapılacaksa yapıyor, transfer edilecekse ediyor işte her neyse. Sonra neydi? Hatırlıyorsanız şeyi, ne zaman switch yapılır? İşletim sisteminin tekrar karar vermesi lazım. Kim devam edecek? Priority schedule'da kim devam ediyor? Priority yüksek olan alır diyor. Eğer I/O için bekleyen yüksek priority birileri varsa ve data da hazırsa, dolayısıyla kuantuma devam eden birisini kesip diğerini çalıştırmaya devam edebilir.
Hocam kuantumu kestikten sonra tekrar değiştirir mi? Hani kullanana kadar tekrar hani yerinde sepetinde yerinde şey yapar mı?
Eğer scheduler tekrar aynı prosesin devam etmesine karar verdiyse arta kalanını tamamlayacaktır o. Ama başka birisine geçtiyse o ortada kesilecek.
Yani priority'yi tekrar değiştirir mi? Kesti anlamında.
Şimdi her interrupt gelişinde priority adjustment'lar nasıl yapılıyor? Bu adam diyor ne kadar çalıştı? Kuantumun ne kadarını kullandı değil mi? Ona göre bir ayarlama yapacaktır ama bazen kendi elinde olmadığı için şeyi kesiliyor. CPU kullanımı kesiliyor. O zaman onun suçu değil. Yani ben zaten çalışmaya devam edecektim. Hem zaten erken kesilmesi demek priority'nin artırılması demek. işine gelir. Başkası 60 falan oluyor. Hayır, orada başkası kestiği için bir itiraftan dolayı onun prioriterini arttırması doğru değil. Bunların hepsi karar ya, böyle yani tabii ki olmaz, şöyle olur falan filan, çok fazla demek istemiyorum. Hepsinin artıları var, eksileri var.
Algoritmaya dayalı bir şey değil mi?
Tabii ki evet, işletim sistemi tarafından schedule'ın algoritması bu. Ve tek başına çalışan bir şey değil bu priority adjustment. Başka taraflarda olacaktır ama temeldeki fikir birazcık şey gibi yani, adam zaten I/O bağım, çok riskle uğraşıyor. Biraz bu şey tamam, priority düşük olsun falan diye düşünebilirsiniz bunu. Hayır, eğer öyle yaparsanız sizin backup olan uygulamanız, backup çünkü çok I/O bağım bir şey. Sürekli diske bir şey yazacak değil mi? Bir blok yazıyor, bekliyor, blok yazıyor, bekliyor. Eğer onu siz priority'ni düşük tutarsanız interaktif prosesler hiçbir zaman onun backup'ı almasına izin vermeyecekler. Backup almak uzayacak, günler sürecek. Onun priority'sini yüksek tuttuğunuz zaman zaten devam edemiyor adam. Değil mi? Zaten devam edemiyor. Yani alıp CPU bağımlı bir şekilde kullanamıyor. But this is how the priority adjustment, this specific algorithm works. Okay. So there are many versions of this priority adjustment algorithms. Another one is priority classes. Instead of assigning a specific priority to a process, you assign them to a class. Let's say you have 1, 2, 3, 4 classes. Okay. So you don't have priority numbers, you have classes. So all the processes in this class, priority number 4, has the same priority. So you are running a round robin within this class, and there is another round robin within this class, and there is another one. Without having all of these processes blocked, you don't run anything in this priority. So you need to finish all the priority for processes first, then these, then this, then this. So instead of having specific priority numbers, you have priority classes. So you have separate queues for each priority level, and each queue runs a round robin algorithm. Okay, so you switch to lower level priority queue when the upper level queue is empty. Without finishing all the higher level priority jobs, you don't go to the lower level. Okay, they all have to be finished, or they all have to be blocked. So this is called run queues. Each queue is a linked list. Okay, sometimes each is a linked list or circular linked list. Okay, because that way, circular linked list. When you are done with this one, you start with the beginning again. So when you do the priority adjustment, remember the priority adjustment, we increase and decrease the priority values using this kind of calculations. With this one, you don't increase or decrease the priority of a job. You move to a different list. You may want to move this from this list to this list. Okay, so you just change its queue. You lower its priority to this priority level 3 sometimes. So there are two types of doing this priority aging with this run queues approach. If you don't have many processes, okay, you keep a counter for each process and increment this priority counter at the clock interrupt at some limit and increase the priority. So you do your adjustment with respect to each process, one by one, if you don't have many processes. But if you have many processes, then doing this is very expensive because you have to adjust the priorities of each process one by one. Instead of adjusting the priorities of each process one by one, you do periodically move each list to the next level up. So you change the priority of the whole level. So just take this out. Okay, take this out and connect this one at the end of this process, connect this one here, So those two priority levels are merged together. Now, instead of adjusting the priorities of each process, so you are adjusting the priority levels of the whole queues. So that's the second approach. Lots of processes and you have many queues, periodically move each list to the next level up. So this is how you do the priority aging with this kind of scheduling algorithms. If you don't have many processes, then you can do this. You can do it with the with respect to each process. But if you have many processes, thousands of them, you don't want to do priority adjustment for each one. So you put them into priority classes and move the classes up and down, merge them or separate them to different levels. Okay. So this is another approach for doing the round queues. Okay, any questions? So priority adjustment is without priorities. Without priorities, it is very difficult to keep the system balanced. There is at least a problem with the, how do you adjust the interactiveness of the system? How do you adjust IO bound versus CPU bound systems? So you need to assign priorities. When you assign priorities, you need to keep them updated with respect to how they use the CPUs. So these are all have to be done with the CPU schedulers. Okay, so this is called priority scheduling with levels. Again, instead of adjusting the priorities, sometimes we may say that let's adjust the quanta. Okay, don't use a single quantum time for the whole system, but assign different quantum times for different processes. Okay, so many processes need just a little bit of CPU time. Okay, so for those, maybe we should keep them. We should keep the quantum time very small. Okay, but for some of them, they might use the CPU even more. Okay, so we know that process switching is very expensive, and I should keep my number of process switches to a minimum. Process switches can be expensive. Don't do them too often. So the solution is, okay, I need to keep my processes interactive. For those, I need smaller quantum times. But for some processes, they don't have to be interactive. Okay, so I can give them longer quantum times. Okay, so the top priority queues have 1 quantum. Okay, and the second queue 2 quantum for second queue, the lower priority, and for the lowest priority I have 4 quanta. Okay, so that means that for the higher priority jobs, who are the higher priority jobs? Those are the interactive jobs. They have a very small quantum. I can do, if I am running this, let's say these are interactive processes, and I run a round robin between these 3. Their quantum times is very small, just 1 quantum, okay? But these are the second priority ones. These are lower priority processes, and they are not interactive, okay? They are doing some CPU bound processing. For these, I don't have to keep very small quantum times. Their quantum is larger, so that they don't switch much. Since they are not interactive, they are low priority. For the low priority tasks, I give them larger quantum times. For high priority jobs, I give them smaller quantum times. Okay, top priority 1 quantum, second queue, the second priority 2 quanta, and the third one is 4 quanta. So this, instead of adjusting their priorities, this one is using both adjusting priorities and adjusting their quantum times. Okay. Any questions? And this third approach, this approach here, okay, this is something to do with the aging. Initially, we have very small quantum, short quantum at high priority, okay? And when our process starts using too much CPU, I need to lower their priority. When I lower their priority, I increase their quantum time. Long quantum at low priority thereafter.
Hocam prosesler arası switch'in neden böyle bir farkı var? Yani sonuçta sadece register'larını kaydediyor, işte PC program kantını kaydediyor. Hepsinde aynı şey değil mi?
Evet, hepsinde aynı şey, hepsinde de pahalı.
Ama burada farklı, daha birisininki az diyor, birisininki çok diyor.
Hayır, şurada proses switch'ten kaçınamıyorsun çünkü interaktif kalmak zorunda bunlar. Tamam mı? Yapmak zorundasın onu. Ama burada yapmak değilsin. Bu backup alıyor, bu pi sayısını hesaplıyor, bu bir tane nümerik analiz yapıyor. Ya burada çok fazla switch yapmak zorunda değilsin. Niye switch yapıyoruz, niye preemption yapıyoruz? Biz interaktif kalsın diye, değil mi? Eğer her bir proses birer saniye CPU time kullansa, bir saniye sonra switch yapsa, switch yapma sayısı çok daha az olacağı için CPU daha iyi kullanmış olacak. Ama interaktif proseslerde, high priority proseslerde bunu yapamıyorum. Mecburen o ödedi yemek zorundayım. Switch yapmak zorundayım. Dolayısıyla bunların kuantumlarını kısa tutuyorum ki interaktif kalsınlar. Ama ortalıkta interaktif olacak bir job yoksa şunların kuantumları yüksek. Birer saniye kullansınlar, önemli değil. Böylelikle şunlar için CPU daha verimli kullanmış oldu. Yani hem bir adam pi sayısını hesaplıyor, bir yandan da bir nümerik analiz yapıyorsa aralarında proses switch yaparak boşuna CPU time'ini yememiş oluyor. Yani low priority'lere daha yüksek kuantum veriyoruz. Hatta batch sistemlerde ne yapıyorsun? Batch sistemlerdeki kuantum time ne kadar? So how much is the quantum time for the batch systems? It is infinity, right? You will run as much as you like until you are blocked. Since the batch systems are the lowest priority, batch tasks are the lowest priority items. They don't have to be interactive because they run for 2 hours, 10 hours, one day. Okay, so we don't assign them any quantum. We say that if you have the CPU, okay, run as much as you can because there is no interactive system in this operating system. Okay, so that's as long as you can go for the lowest priority tasks. Okay, so this is the varying quantum. These are all have to do with adjusting the priorities of the tasks and adjusting their quantum times. Okay, so we said that interaction is important. We are looking. Remember where we are at actually. Let's remember what we are doing. We are doing this. We are trying to go over the scheduling for the interactive systems. Okay. So with the interactive system, there is this issue of quantum time. Without the quantum time, I wouldn't have any interaction. Without the preemption, I wouldn't have interaction. So we said that with the simplest priority scheduling, I would run into problems. So I have to adjust my priorities, maybe make them higher, maybe make them lower. And along with adjusting your priorities, maybe I can adjust my quantum time too. Let's look at helping the interactive process even more by running some other algorithms. We say that, okay, how do I know that if a process is interactive or not? Okay, how do I know that the process is interactive or not? I would ask the programmer to mark their process as interactive or not. That would be one way of doing it. Or there are some systems. Okay, they look for the signs of the user input. If the process is running, okay, and while the process is running, the user is interacting with the keyboard or moving the mouse, that means that process is an interactive process. So increase the priority of that process or the lower its quantum time. Okay, so this is what this CTSS did. Okay, if a user types a carriage return or presses a keyboard key, then the priority of that process is increased. Okay, priority of that process is increased, and this algorithm was used in this system. So the problem with this system is that if somebody is always pressing this enter button all the time, even though he doesn't need to enter it, the system by mistake will increase the priority of that process, and that will hurt the whole. That will make that process run faster because it has higher priority, but that will hurt other processes in the system. So there is a problem with this kind of approach. We don't use this approach with today's computers actually. Okay, and actually when I use this computer, I have at least 100 processes running. So if I move my mouse, what kind of process should I increase the priority? I don't know because there are 100 systems. So this approach is not very useful for today's personal computers actually. Okay. And so how do we assign priorities? That's what we said actually. Interactive services have higher priorities. Kernel processes have higher priorities. So the adjustment can be, or the priority assignment can be done using different techniques. We don't know. Sometimes if you use a computer by paying money, okay. Let's say I am paying $10 per hour, okay. If I pay $10 per hour, okay, maybe my priority is 10, but if I spend $20 per hour, maybe my priority will be 20. Okay, so with this kind of systems, there are some higher priority users because they are paying more than the others. If I don't want to pay any money, maybe my priority, okay, I don't want to spend any money, my priority will be just 1. That means that if there are no tasks for the computer to run, then it will run my priority, my job, because I didn't pay any money. Okay. Sometimes the users might want to lower their priorities. Okay. The user can lower the priority of their own process. Do you know how to lower your priority in Unix? How do you run your Unix job with a lower priority? Do you know how to do it? I think I tried something here. Okay. So this is my process table. Okay, this is my process table. I have 1, 2, 3, 4 things running here, and this is my user ID. These are my process IDs. Okay, and these are my priorities. Their priorities are all the same, 20. In Unix, higher priority means lower priority number. So if this number is small, that means that I have a higher priority. I have a higher priority. So if I run something, let's say, okay, let's say I am, okay, CD ls minus r. What does this do?
Recursive olarak.
It lists all the directory contains recursively, so it's going to take a very, very long time to finish. So let's go there and let me see. All the, so ls is running, okay. This one is running, and its priority is 20. It is the same as the other ones. But if I know that this one is going to take very long time, so maybe I should not use that much CPU. Maybe I should not use very high priority. I would say that I will be nice, and this utility nice. When you nice your process, it will lower its priority. Okay. When you say nice ls, it means that okay, I will lower my priority. You can let other processes run instead of my process. If the CPU is available, I will use it. So I will do this nice ls. So it is running. Let me take my priority. See, this one is 10. So my priority is lower now. It's not higher. It's lower. The others have higher priorities. The others have higher priorities.
Priority'nin yanındaki de değişti hocam. O ne oluyor?
Hocam
Hangisi değişti?
Şu
mu? Neyin ne olduğunu bilmiyorum. Home page'ine bakın. So these are the priority numbers. But if I cut it, and if I do this twice, I want to be extra nice and nice, okay? So it is, so the speed of LS doesn't change much, why? I lowered my priority, it is still running there. When I do this, time, okay, let me do this, and, well, this one. Okay. But do you know this? Let me try to do this thing to open. No, this one and 2, right? Was it? No. I am trying to redirect the error too. No, I couldn't try it.
Nasıl?
How about this one?
Ampersand koyuyorduk galiba hocam.
I am trying to measure how long it takes to. Okay, let's do this. Okay, so it takes. So this is very. So I am trying to go to a place where it takes some time to. Let me maybe. What do I have here? Maybe. Bin directory. That is again to it's too fast. Maybe lib directory. Or it is taking the same time. I was trying to show you that. I mean, it doesn't matter. It doesn't matter if I make my LS extra nice, okay? I see that my process is running very, very fast. That's the question. Why do you think that it is running so fast? I lowered my priority. See, my priority is now 0. Right? It is 0. But it is still running very, very fast. Why? Because there is nothing to. That's the correct answer. Because there is nothing else to do. If the computer doesn't have anything else to do, it will run the lowest priority job 100% of the time, right? So the priority doesn't mean that my process should run slower. It should run my process slower if there is nothing else to run. Okay? If there is nothing else to run. So is it done? No, it is still continuing. So I wanted to show you. I wanted to show you the differences between two processes if the CPU is all taken by other processes, but I couldn't find a good example here. So this is how you lower your priority in Unix. So there are ways of lowering your priorities. The users can lower their priorities on their own, sometimes to avoid competing with themselves. Okay, this is not that important. I'm taking the backup, and this is a lower priority. I can adjust it that way. You cannot increase your priority though. Why? You can lower your priority, but you cannot increase your priority. Why?
Zaten en düşüğünü veriyordur.
Olabilecek en
User için en düşüğünü veriyordur.
See, this is Unix priorities. It says that okay, this one has a higher priority. This one, okay, no, okay. But is the highest priority job here is this one, okay. And lowest priority is 75, right? It's this one. So the system related things are higher priority, and Other things are lower priority. There are different levels of priority levels. I can lower as a user, I can lower my priority, but I cannot make it higher. Why? As a user, I cannot do it otherwise. If everybody is able to make their priorities higher, that means that everybody would do the same thing, right? I want my process. Remember, processes are competitive, okay? They all wanted to use the CPU most of the time, all of the time. They think that the whole computer belongs to themselves, okay? So if I let the processes use the CPU with a higher priority level, they will choose to do so. So I cannot let them use the CPU all the time by making their priorities higher. That's why Linux or Unix doesn't provide any way of hiding, making your processes priorities higher. You can only make it lower, okay? You can make it only low. That's why this one says that, okay, users can lower their priority on their own processes, because if I make my process priority lower, maybe my other task will run faster. Okay, that's what I mean. Any questions? Bir soru sorunlara verelim en son.
Hocam, iki prosese aynı priority neye göre veriyorum? Yani bunu sistemi neye göre seçiyor? Diyor ki sen de aynısın, ben de aynıyım. Neye göre
Tüm
veriyorum?
kullanıcıların A isminin A ya da B olmasının arasında bir fark yok. Tüm kullanıcıların tüm prosesleri aynı priority'yle başlar.
Sonra.
Neyle gelişir ama mesela şey var. Adam arka planda çalışan demon'lar var. Ne yapıyor mesela? Network'ten bir şey geldi mi gelmedi mi ona bakanlar var. Ya da arka tarafta şeyler var. Bir şeyler çalışıyor mu çalışmıyor diye kontrol eden bir tane proses var. Sürekli olarak kernel sağlam mı değil mi diye bakıyor, tamam mı? Eğer kernel'den haber gelmiyorsa, kernel çalışmıyorsa bir tane daha kernel çalıştırıyor. Bunun priority'sinin çok yüksek olmasına gerek yok. Yani sistem task'i ama sistem için çok önemli bir proses ama bunun priority'si olabildiği kadar düşük. Dakikada bir çalışsa yeter onun için. Onun priority'sini düşük tutuyor. Ama interaktif kalması gerektiği, mesela mouse ile ilgilenen, interruptlarla ilgilenen bir tane task var orada. Onun priority'sinin yüksek olması lazım. Kararlar bunlar. Sistem tasarı zamanında veriliyor bunlar. Ama tüm kullanıcılar, tüm proseslerin hepsi aynı priority ile başlıyor. 57 olmuş ya, geç kalmışız. 10 dakika karar verin, böyle gidelim.